How to solve systems of differential equations. The article, How to Solve Differential Equations, goes over different types of differential equations and how to solve them. However, it only covers solving single differential equations. This article takes the concept of solving differential equations one step further and attempts to explain how to solve systems of differential equations. A system of differential equations is a set of two or more differential equations in which the solution depends on how all the equations interact. This article assumes that the reader understands basic calculus, solving single differential equations, and linear algebra. The most important concept to know from linear algebra includes solving systems of equations, working with matrices, and calculating eigenvalues and eigenvectors. To keep things simple, this article will cover how to solve a system of differential equation with two differential equations and only consider the homogeneous case. Part 1: Calculating eigenvalues and eigenvectors. 1. Write the system of differential equations in a matrix form. Notice that the A matrix contains the coefficients of the two differential equations. It is important to write the A matrix correctly. 2. Find the eigenvalues of the A matrix. When solving for the determinant of the 2 by 2 matrix, a quadratic equation is obtained. The two solutions of the quadratic equation are the two eigenvalues of matrix A. The solutions will be one of the three cases. The eigenvalues are distinct, meaning that the values of the solutions are real and different. The eigenvalues are complex, meaning that the solution contains imaginary value. The eigenvalues are repeated, meaning that both the solutions are the same value. 3. Find the eigenvector of the A matrix for each eigenvalue. For a system of two equations, there are two eigenvectors, one for each eigenvalue. Remember to keep eigenvectors simple, because they're easier to work with. 4. Choose the form of the general solution based on the three cases. A general solution is the solution with unknown constants, and it doesn't take into account the initial condition. See Part 2, 3, and 4 for writing general solutions. Part 2: Distinct eigenvalues. 1. Plug in the values according to the formula to obtain the general solution. Include the unknown constants, C1 and C2. Part 3: Complex eigenvalues. 1. Plug in the values according to the formula above. Choose one of the eigenvalues and its corresponding eigenvector. 2. Separate the exponent into the real and imaginary part. Follow the rule of exponents. 3. Use Euler's formula to get rid of imaginary exponent. This transforms the imaginary exponent into sine and cosine functions. 4. Distribute the sine and cosine terms into the eigenvector, v. 5. Separate the equation into the real and imaginary parts. 6. Write the general solution according to the formula. Part 4: Repeated eigenvalues. 1. Find the p-vector using the condition above. Remember to keep p-vector as simple as possible. Usually, this means choosing p1 to be 0. 2. Write the general solution according to the formula. Part 5: Initial value problem. 1. Plug the initial condition into the general solution to solve for the unknown constants C1 and C2. Most problems are given along with an initial condition. The solution where the constants are known is called the particular solution. This solution is more specific because it takes into account the initial conditions. Tips. To appreciate differential equations, think about the different things engineers can do using this concept. Differential equations can be used to model the motions of objects, the rates at which chemical reactions occur, and the current in an electrical circuit.